and V and W are the feet of the angle bisectors of DAC and DAB. Oh, that's weird. The intersection of VW. Oh, okay. So let's draw the angle bisectors. Oh, and now I remember this one. This one is really interesting, actually, this problem. So yeah, it's not hard to prove. Basically, by the angle bisector theorem, it turns out it's really easy to see that VW is parallel to BC. It's like, so yeah, clearly BW has to be parallel to BC if you use the angle bisector theorem twice. Let me draw something like that. And then M is the intersection of VW and AB. So really just the midpoint of VW, right? So we start out knowing a lot of information here. So we have the midpoint of VW basically. E and F are the midpoints of AC and BC. So like you find out a bunch of obvious things, but then the conclusion is not obvious. So those are two midpoints. And then you want to draw the intersection of FM and AC. I think they mean, well, let's see, F. Oh, because I switched E and F. Okay, let me. So this is E, this is F. So EM and AB intersect at this point. So we have Y and Z, and I think it's even true that YZ is parallel to BC. So we get a lot of like things that we know, but then the thing that's not obvious is to show that YZ is equal to AD. So, all right, so I'm going to hide a lot of stuff. So yeah, YZ is equal to AD. Let me see if AZDY is cyclic. Nope. So yeah, what happens if we play around with the triangle a little bit? It's a really weird, like if we make it a really flat triangle, then that almost doesn't look true. Like YZ is equal to AB. It looks like AD is longer, doesn't it? Doesn't it look like AD is longer than YZ? Maybe it's just an optical illusion. 2.37. Oh, they are the same. That's like an optical illusion, isn't it? Doesn't AD look longer? It looks longer, doesn't it? How could they be the same? There's no way AD equals YZ. How could that be? I guess it's true. Huh. That's interesting. All right. Or if you make it like a super tall triangle. Yeah. So I think we can get to the length of YZ kind of by using ratios a bunch of times. But I think for AD, we might want to like break it up into two segments. So like YZ, we should be able to get with ratios, right? Because EF is half of BC. And then for YZ, yeah, can we find like YZ over EF somehow? That would be like MF over MY. I mean, we could probably use Menelaus somehow. So basically, if we use Menelaus, then we have AF over AZ times ZG over GY times YM over MF. It's 1. Oh, that's kind of trivial. We have to show AV over VB equals ZY over BD. And BD is half of BC. So interesting. Well, so ZG over BD is the same as AZ over AB. Midpoint of YZ. So that would be G, right? Oh, the midpoint of AD. And that's, yeah, that would be H. Okay. So yeah, we want to show AH is equal to GZ. We need GH is equal to GY. I don't think that would be true because then that would mean this would be a right angle and it doesn't. Let's see. I don't think it's a, yeah. I wonder if triangle AFH is congruent to triangle ZMG. Yeah, no optic collision this time. Oh, GY equals MD. Yes. So yeah, I wonder, let's see. So no, those aren't congruent. Is VH parallel to BG? Use the parallel. No. And G. I'm trying to find congruent triangles. Oh wait, I think it would be ZGY equals HD, right? Yeah. Let's see, that's 1.54. I wonder if it might make it easier to let EZ and FY intersect BC. Then I think you might be able to just bash the problem, actually. Because then, you think about it. EV intersect, EF intersect BV. Yeah, we can do that. Hmm. Are there any congruent triangles we can find? AZ intersect BC. AZ intersect IS. IZ. Wait. Oh, IZ intersect BC? Maybe triangle AGY is congruent to, actually, let me think about this. AIJB is a parallelogram. Ah, that's good to know. It looks like dm equals dk. No, I don't. I would be very surprised if dm equals dk. Oh, dh is equal to dk though. Maybe that's what you were saying. Yeah. And then it looks like this is a parallelogram. So yeah, with all these parallelograms, it looks like that would solve. Yeah, so we have so many parallelograms here that it looks like it has to be solved. Yeah, because IH dk is like a parallelogram. Yeah, it's all parallelograms from here, I think. So let's see. Yeah, so is it so? Oh, is this a rectangle? Oh yeah, because they're both angle bisectors. So AD is equal to IJ, and then IH is equal to GZ, so that pretty much solves it. Yeah, but yeah, but let's see. We need to show. Yeah, so since these are both angle bisectors, this is a right angle. But yeah, how do we show? Oh, but it's yeah, it's obvious because this is a right triangle right here, and then you're reflecting B across the midpoint. So yeah, then that's a rectangle. But how do we show? Is it obvious that IH? So let me delete K. Is it obvious that IZHG is a parallelogram? So how do we know IZ is parallel to HG? I think that's the final step that we need. Yeah, it doesn't seem that obvious to me that IV over DV equals VZ over AV. is what we have to show. Asrianch, thanks for joining. So let me check if this is cyclic. No. Yeah, okay. IV, oh, where IZ intersects BD. Okay. So yeah, how do we show that this is parallel to this? Yeah, we want to show, there's about an hour left. A little less than an hour. So yeah, if we want to show they're parallel, we want to show that, like, we want to show that AW over WY equals JW over WD, which is, and yeah, AW over WY. So we want to show that AM over MG. Let me think about this a little bit. I think I'm a little confused. So JW over WD is equal to HM over MD, and YW over WA is MG over MA. I'm confused now because do we really know that those are parallel? Maybe if I change, like we're saying JY is parallel to HG, right? Is that true? I think it is true. Yeah. But yeah, it doesn't seem that obvious to me. So I'm going to go back to IV over DV. Oh, because I was dividing instead of multiplying. Equals VZ over. So IV over DV. See, what's really confusing, you said we want to show, so IB over DV, that's HM, okay, we want to show that HM over MD equals MG over AM. Maybe we could use homophogy, because like, so HM over HD is the same as HM over HI or HJ. I think we're close. Hey, Anurag, thanks for joining. It's all right. Glad you could make it. So yeah, we have about an hour left. And I thought we were close on this problem, but we might have a little bit more. Okay. Yeah, we want to show this is a parallelogram. So dm dk is equal to hi. But dk, how do we know that dk is equal to hi? Because we don't know yet that this is parallel to this, right? We still have to prove that iz is parallel to dh, right? Yeah. I'm not sure. I'm trying to use the ratios that Ravi said earlier. Oh, you know what? I think it might be, I think it might not be that hard. So yeah, if we show dk equals hd, that would solve it. So, but you know what? I think, so we want to show, I'm going to write this down on a sheet of paper, but I think we might have it. I think it might just be, so that's dh over dm is equal to, so that would be zy over vw. So dh is equal to ah. So we want to show ah over dh over. I think this is very close. So I think it might just all be ratios from here. Yeah, it's equivalent to that basically. So that would be pf over dv is equal to okay. Yeah, okay. So I kind of like the way Ravi wrote it. MH times AM is MG times MD. I wonder, let's see something. So if we draw the circumcircle, that would be like the power of m with respect to this circle. And that this would be like the power of m with respect to this circle. Is that? Yeah, can we get a good circle? Is VH perpendicular to AH? I don't think so, because then WH would have to be perpendicular, right? Because everything's defined symmetrically. Yeah, it's not true in general. Sorry. Is DE parallel to ZF? Oh, I think it might be. Ah, it looks like it is. That must be something we just missed. Oh yeah, because it's the medial triangle. Yeah, so that's obvious. So I wonder if we can somehow, can we make a circle that's like tangent? Like that, for example. And then can we make another circle that's tangent? If we're saying it should be the same point. I wonder if we can use homotheties, because basically we want to show that MD over MH is MG over AM. what if so for mg over am, that's not a right triangle, that's the problem. But by Pappus, so how do we use Pappus? Actually, you know what? Because let's see, we want MD over MH. Basically, we could look at the medial triangle instead. So basically, we're saying a homothety. We want MG over AM is MD over MH. So we're saying M corresponds to itself under if you do a homothety of these two triangles, right? That's basically what it's saying, right? Oh, we are? Oh, since M is the center of homothety of those two triangles, then we have those ratios are the same. Okay. And so then it follows. Okay. All right. So I'm going to write this up. So, yeah. Yeah. All right. I didn't even realize what I just did, but it happened to work. All right. So first I'm going to show that BW is parallel to BC. So we have by the angle bisector theorem, we have AV over VB is equal to AD over DB is equal to AD over DC, which is equal to AW over WC. And that implies that VW is parallel to BC. And then can we also show YZ is parallel? So is that trivial? That YZ is parallel? So that implies M is the midpoint of VW. So i.e. Okay, so John has an idea using Pappus. So IE is parallel to VM, and ED is parallel to VZ. I'm a little confused. How do we know ZY is parallel? Is that obvious? I guess it should kind of be obvious, right? Because since EF is parallel to VW, then it's just ratios, right?
Yeah, I think Siva's theorem would do it.
Okay, would prove that it's parallel. So C, and then by Cheva's theorem, also YZ is parallel to BC. Okay. And then, so AYZ and DEF are homothetic at point M. So that means that dm over mh is am over mg. And now let dv and dw meet ef at ai and ha. Okay. So this is going to be a right angle. I don't even know if we need that though, but let's see. So we want to show that IZ is parallel to this, which is the same as saying AV over VZ. Yeah, so I'm going to rewrite this. So this basically, since we know this, this basically means that so dm over mh, that is dv over vi. And am over mg is av over vz. And that means that IZ is parallel to AD. I was a little confused, so wait till I'm going to read it again in just a second. So we have IZ is parallel to AB, and so HGZ is a parallelogram. I don't even know if we needed that this is a right angle, right? So, oh yeah, I think we did because, yeah, because we're using that HI is equal to HD. So we have angle IDJ equals 90. Since DV and DW are both bisectors. And then that means that DI, DH, HD equals HI equals HJ. Give me just a second. So we have AD equals 2 HD 2HD equals 2HI equals 2GZ is equal to YZ. And that solves it. So what was your way of doing it with Pappas? Let's see. I'm going to go back and read it in the chat. We have about 30 minutes left. So IE, I think you're using it in a degenerate form, right? IE is parallel to VM, and ED is parallel to VZ. Okay. So it's like we have kind of a parallelogram here. And IVD and ZV. I don't totally understand. Thus, ZI is parallel to DM. Are you saying like 3? So for Pappas, it's like you have one segment with 3 points and then another segment with 3 points, right? And then let me go back. So you said IVD and ZVE. Or I don't think you mean ZVE. IVE and ZVM, I think you mean, right? IVD and ZME. Okay, so basically you're saying VM and IE intersect at the point at infinity. And then DM and IZ would intersect. We want to show they intersect at the point at infinity. So IVD and ZME. Is there one more parallel? So then we have ZM. Yeah, what are the 3 intersection points all like points at infinity? So IZ and DM. VZ is parallel to D. Oh, because VZ is parallel to DE. That's right. So we have one parallel, 2 parallel, and then we have a 3rd parallel, which I think I just forgot, but M, IBD, and ZME. So these are parallel, these are parallel, so the 3rd one has to be parallel. That's kind of interesting. I don't think I've ever seen Pappas used like that before. Interesting. All right. So I will move on to this problem. So we have a cyclic quadrilateral, ABCD. And diagonals meet at a point P. And AD and BC meet at Q. So this is P. I'm just curious. I'm just going to take a quick look at the next problem. Oh, this one actually looks kind of interesting, but I think this one might be easier, so I'm going to do it quick. So you have a cyclic quadrilateral, and then we draw the rays AD and BC, and they meet at Q. Yeah, I've never seen Pappas used that way before, where you have like 3 parallels like that. So this is point Q. We draw the bisector BQA. And it meets AC at R. And then we draw the bisector of APD. Let's see. Yeah, I want to make it look a little nicer if I can. So yeah, it almost looks like P lies on the angle bisector. So I think that looks a little better. Yeah. So it meets AC at bar. So this is R. And the internal bisector of APD intersects AD at S. And we want to show RS is parallel to CB. So can it just be bashed with ratios? Let's see. So we have one angle bisector, then we have another angle bisector, and we just want to show RS is parallel to CB. So we just want to show AR over, is this trivial? We just want to show AR over RC, because we know AR over RC is AQ over QC. Yeah, I think this is trivial. And then we want to show AS over SD is AP over PB, which we just want to show AP over PB. Oh, wait a sec. AR over RC is AQ over QC. And then AS over SD is AP over PD. So we want to show AP over PD is AQ over QC. And is that trivial? Yeah. And AP over PD, since those should be BP over PC, yeah, is that obvious? It feels like it. Oh yeah, it does look like they're perpendicular. So we have BP times PB is CP times AP. So yeah, like shouldn't that, wait, in this picture it doesn't, okay, we want to show RS is parallel to CB. Okay. Yeah, it feels like that fact should be trivial, but I just can't prove it. AP over PD is AQ over QC. Should that be obvious? I don't know why it's. So we could just keep trying to use PowerPoint. So we have AQD. Let me write this out on paper. Maybe it's just obvious. So AP or yeah, that's true. For PC, and then we have AQ over QC is QB over QD. So we want to show QB over QD is PB over PC.
Yeah, it's actually trivial by some sine law.
Oh, really? But should we have to use like are there just some similar triangles that could prove it, or do we have to use that?
Yeah, I think we need to use that because two of them are supplementary angles.
Yeah, because angle BCP is like 180 minus BBQ. So yeah, I kind of see what you're saying. But yeah.
Yeah. If you just label PDA as beta and PAD as alpha, I think AP upon PD equal to sine beta upon sine alpha is the same as what was the other one? AQ over QC.
Yeah, I see. Yeah, I see what you're saying. So, yeah. So basically, yeah, you have these two triangles right here, but this angle is 180 minus that. So basically, we have, yeah, AP over PB is sine of
if you want similar triangles, you can consider the reflection of Q over C.
the reflection of Q over C.
Yeah,
Yes.
because that 180 minus would be, I mean, supplementary would be implying similarity.
Yeah. So I'll just do it using the sine wave just for now. So AP over PB is sine of PDA over sine, or I'll say sine of BDA over sine of CAD. And that's sine of BDQ over sine of CBD. And that is BQ. Let's see, what did we want? We wanted AQ. Oh no, I didn't need that one. So CAD stays the same, but BDA is BCA, which is ACD. So we still want this to be CAD, but BDA, this would be BCA. So I'm just going to write it out one more line. So sine of ACQ over sine of CAD. And that is, yeah, I'll change in just a sec. So that's PB. That is AQ over QC. And this might make it better. All right, thanks. And then once we know that, by the angle bisector theorem, we have AP over PD is equal to AS over SD. And AQ over QC equals AR over RC. And so this means that AS over SD equals AR over RC, which solves the problem. All right, so let's move on to the next one. That was an easy one. Other ways to draw the parallel through P to AB to meet BC, and that parallel would be tangent. Okay, so then yeah, that would help avoid using trigonometry also. Interesting. All right. So we have 15 minutes left. Let's see if we can solve this problem. We have a triangle ABC and a circle O. So O is the center of the circle. And we draw the parallels to each side. Whoops. So this is O. And then let's draw some parallels. Let me make it a little better in just a second. Yeah, I want both of the parallels to be, yeah, something like that. So, yeah. All right, so we have BE and AC, BE and CF. And we want to show the Euler line of ABC. So let's draw the orthocenter. Say H. There's the orthocenter. We want to show it is the radical axis of OBF and OCE. So yeah, the problems today were a little bit easier, but they didn't use a lot of like stuff about configurations, which is kind of good, I feel like, because a lot of those problems, it's just like about knowing like a lot of stuff. Whereas, yeah, these were a little bit easier though. So yeah, we want to show HO is collinear with this point. Which is kind of interesting. So we have a couple isosceles trapezoids. ACEB is an isosceles trapezoid, and so is ABFC. So how do we show H has the same power with respect to those circles. Is EO equal to EF? Well, I doubt it, because that would mean, I don't think EOF, well, OE is equal to OF, but I don't think in general those are equal to EF. Yeah. I would be very surprised if that were true. Yeah, so OE is equal to OF, but they're not equal to EF. I wonder if OBE and OCF are similar. I don't think so, because here OCF is, yeah, they're not similar. Okay. I don't know if we could show OH is perpendicular to DG. Or maybe we could draw the centroid, because like the centroid lies on the Euler line. The 9-point center lies on it. I don't know if those would help. So any one of those, really, we want to show they have the same power with respect to those two circles. Maybe we could use Casey's theorem. I kind of like using Casey's theorem. So we could take the difference between the power of a point with respect to one of the circles in the circumcircle. Yeah, let's go draw the centers of these again. So but we would need to find the distance from that point to BF, which I'm not sure would be that easy. So yeah, BOF. So OB is equal to OF. And so that might give us some like angle bisectors. Because like if we drew this point right here, we have angle FIO is angle BIO. So let me call it J, just because it bugs me. So this is an angle bisector of BJF, and it's also an angle bisector of CJE. So I wonder if BJE is similar to CFJ. I think that might be true. That this is similar to this. Okay, I'm going to delete these centers. Let me check. That's 144. This is also, yeah, these should be similar. How do we prove that? So yeah, I can prove that angle BJE equals angle CJF. Can I also show anything with ratios? Yeah, it's so. So we want to show BE over CF equals BJ over CJ. Yeah, that would mean a spiral similarity takes EJB or JEB to JFC. So yeah, basically, I mean, we want to show H lies on that angle bisector. Maybe it's even the isogonal line lemma. Yeah, how do we show that H lies on the bisector of all those? Um, so let me go back to drawing the center. Like we know that, so these circles kind of have like similar triangles in them. So HD squared minus the radius squared. We want to show it's the same with this one. I wonder, like, if we draw this point, is there anything? I doubt that D is the antipode of A. Yeah. AOC and BOA are congruent. Are you sure you meant those? So I don't think those aren't congruent in general. AOC and AOB and EOC. Interesting. Okay. That is good knowledge. Yeah, because ABEC is an isosceles trapezoid. So that is good to understand. So yeah, I wonder if we knew that these are similar, would that solve the problem? I still don't see how to use point H. Or is there, do you know if there's any like special properties of the Euler line? Um, Yeah, I don't know. I don't know any lemmas about the Euler line, so it's hard for me to say. But I know there must be some. I think there's something about like, yeah. I think there's something with the Euler line and like the anti-Steiner point or something. Like I know, actually I know one lemma. If you take any line through the orthocenter, yeah, let's do this. Let's take this line. If we reflect it over all three sides, it should lie at some point. Oh, but it doesn't look like there's anything special about that point. So this point right here, yeah. Yeah, so they all meet at this point, but I don't know if there's anything special about that point. Well, okay, so yeah, that's really the only thing I know about the orthocenter. Although there might be some other. I mean, we know that AH is twice the distance from O to BC. So maybe that would help us use a homothety. So like AH is 2OD. And AO and HD meet on the circle. But yeah, I don't know how this helps us. That's the thing. All right, so we're out of time today. So yeah, if you guys find a solution, feel free to share it. So for everyone watching on YouTube, thank you for watching. If you want to join us in the future, feel free to email me at mgreenb801@gmail.com. It's in the description of the video, and we meet every Sunday at 8 a.m. US Central Time. So we got through 5 out of 6 problems today, so I was pretty happy with it. And I'll continue doing some more by Jean-Louis Saime. So thanks again, and I'll see you guys next time.